Okay, can you see my slide
Yes.
on your screen? Perfect. So I'm just going to give you, as it says here, an overview of frost protection. This is certainly a complex topic we could talk about for a whole day to really get into details. So just out of necessity here, I'm kind of rushing over topics. But I certainly invite your comments and questions, and if you want to follow up later, that's fine too. I've taken information from a number of colleagues. I see the people on the list there. I'm the only one who's still active in that list. The others are, well, active but retired or have moved on to other positions here. So these are always group efforts with our colleagues. Okay. So here's an outline of what I'll be discussing here. I'll give you an overview of what we call passive frost protection, where we're kind of designing orchards and other crops to be resistant to frost in the first place. Use of sprinklers, just a general overview of water approach to protecting for. Talk a little bit about wind machines, another popular tool. I'll touch a little bit on copper sprays and the whole concept of ice nucleating bacteria, which is something important for us to understand. It certainly presents some interesting potential control measures following this route. And then finally, I'll wrap it up with some of the work that I'm doing where I'm measuring inversion conditions and relating this to predicting where we can use wind machines and trying to manage wind machines better. So this has been a large area of work for me for a little bit more over a decade now. I kind of give you an idea of how this works. It's certainly relevant to your crop and other crops in California and elsewhere. Okay, so let's start off then with some passive frost protection concepts here. But first of all, let's just talk a little bit about what is a frost and what is a freeze. A frost, technically, anytime the air temperature drops below 32 degrees Fahrenheit. And that's the note here about measured at a height between 4 and 6.5 feet above the soil level. Actually is an important thing to make sure we're standardized on how we measure temperatures. I often see growers installing weather monitoring equipment, sometimes just a couple of feet above the ground, and you get very different temperatures when you're at that height. Or I've seen cases where weather stations have been put on top of barns, might be 15 or 20 feet above the ground. And again, you're going to get a very different condition there. So we have to standardize a little bit how we measure things. Freeze, now we're talking about the actual freezing of water within the plant tissue that actually causes the damage. Okay. Now I've shown here a picture of some frosted grapevine tissues. As Ben mentioned, a lot of my work has been in grapes. And so a lot of my pictures come from vineyards, but do keep in mind these concepts are really universal. We can apply them to really any situation that we're dealing with. So what is the freeze injury? What happens? When the plant tissues fall below a critical temperature, ice can form in between the cells. So it's not the liquid inside the cells itself that tends to freeze, but rather ice is forming between the cells. And in that process, water is drawn out of the cells and dehydrates the cells. And then as those ice crystals increase in size, they can also puncture and cell. So it's sort of a combination of just dehydration from water being drawn out of the cells and then the puncturing of the cells as the ice crystals form. So, in practice, it's maybe not important that we necessarily understand that in our management, but it's an interesting to be aware of how this process works. Because it does then relate back when you start talking about ice nucleating bacteria and things that we can do to try to prevent that initiation of ice formation in the first place. We have different types of frost events. Okay, so most of our frost events in California would be classified as a radiation frost. These occur under conditions at night when you have clear skies, very little wind, and then this tends to form a strong inversion. So that blue line there, that represents the change in air temperature with height above the ground. And let me see if I think you guys can see does my cursor show up on your screen, Ben? Can you see that? Okay. Yeah. So notice that here, the way this line is, the slope here the air temperature increases substantially with increasing height above the ground. And that's what we take advantage of with the wind machine. So typically with our radiation type frosts, we tend to have strong inversion, or at least the presence of an inversion. Depending on the location, it may be strong or weak, but we tend to have inversions form. Now, contrast that to what we call an advection frost event. Here, this is often characterized by cold and windy conditions, often cloudy as well. These generally occur when we have a large weather front moving into California from up north, for example, and can occur over very large areas. Here, you can see by that red line, there's very little or no inversion with this type of condition. So it's really important if we are going to use something like wind machines that we have an idea of what these inversion conditions are like. So I'll talk more about this a little bit later. But the key thing is to understand that most of our frost events tend to be these radiation frosts. Advection frosts, when they do happen, can be very damaging, and it's far more difficult to control against them. Both the wind presents problems and the lack of inversion as well. But even within radiation frost, we have two different types of events. On the left is what we call a white frost, or also called a hoar frost, and on the right, a black frost. What's the difference? Well, it has to do with the dew point. So on the left, as that temperature dropped below freezing, it eventually hit the dew point, and then that resulted in ice crystals forming on all the surfaces there. So that's what leads to the white ice formation. On the right, it also got very cold, but it did not reach the dew point, so there was no ice forming. The impact on the plant's the same. You still have the damage occurring, but it's just the appearance is very, very different. So typically in California, we're going to see the black frost type conditions. So just in case you hear those terms, you know what they are referring to. Okay. So types of passive frost protection here, there's sort of a list of things that we can do to hopefully try to prepare our orchards and other crops. Key is site selection, trying to avoid sites which are known to be prone in advance to suffering cold damage. That's our number one option there. If we do have a site, like Ben had shown, that has some issues with cold air drainage, to try to ensure that we can move the cold air off of the site as readily as possible. Soil cultivation and soil water content greatly impact the ability of that soil to store heat and then to release it later in the day. Cover crop management. The cover crop sort of serves as like an insulating layer on top of the soil. And if we allow that cover crop to grow excessively, that can lead to problems with not having very much heat storage. And crop management like nutrition, mulches, go in line, kind of acting like a cover crop would. Covers and wraps, things could be pretty over a crop, for example, and a little bit about bacteria control, like for the ice nucleating bacteria, which I'll talk about a bit more. So here I'll just go into a little bit more detail on some of these things here. So site selection here, there's again a really important very first step to understand what type of risks we're going to have. So here's an example of vineyard situation here in Santa Barbara County. Very clear, these upper hillside locations and the valley bottom locations are going to have very, very different realities when it comes to frost. You can see where the wind machine is located. It has to be down on the valley bottom because that's where it's very obvious. That's where the frost risk is going to be the highest. Up on the hill slopes, the higher elevations, there's very little risk for them to have frost under those same conditions. So again, you can kind of predict ahead of time where the frost risk is going to be. Now, this is for the majority of our frosts when we have these radiation type frost events. But conversely, when we have these rare advective freezes, it tends to be the higher elevation places that suffer the most. So they don't escape necessarily, but just the risk of frost tends to be much less likely, but still can happen. There's just a schematic here showing you how the cold air moves here. So cold air, there's a process called the katabatic flow. Think of it like cold air is more dense than the warm air. And if there's a slope present, that cold air can just very slowly, like molasses, be flowing down and slowly accumulates in the lower areas here. So that's what that blue color represents. mass of cold air, which has sort of become trapped in that little bowl there. And it's pretty easy to predict that, just it's where the cold damage is going to occur and where the highest risk area is going to be. And here's an example then in the avocado planting in San Luis Obispo County, where we had some very cold temperatures a number of years ago. And you can see in this planting, even though it's on a higher elevation, there's still a drainage of cold air that goes right through the middle of this planting. And you can see very clearly where the damage happened. So again, it's really important to, as best as we can, to try to figure out where these cold drains occur and try to make sure that they're not blocked in any way. Probably give them a little more space. Avoid planting right up to the where the drainage areas are, because it's fairly predictable where the damage will occur. And this was a fairly extensive event, as you can see. So luckily, these don't occur too often for us. Now, cover crops, again, this is in vineyards and many other crops, and even now in crops like almonds and pistachios, we're looking far more at implementing broader use of cover crops. Yeah, I think in the your avocado situation, it's going to be a little different. You have different needs for soil management. But I just want to cover the basics here. The presence of the cover crop acts like an insulating layer during the day. So part of our method of warming our crop, our orchard or vineyard during the day is to allow sunlight in the day to heat the soil, the ground surface, to then be re-radiated at night. Well, if we have a cover crop like on that upper left picture, that is greatly blocking the incoming solar energy during the daytime. So we just don't store as much heat. And at nighttime, the coldest temperatures in that system occur at the top of the cover crop canopy. So if we have a tall cover crop, that raises the coldest temperatures up higher off the ground and puts our crop at even higher risk. So how do we avoid having these issues? Well, we do like on the upper right picture or lower left. During our frost risk period, we try to minimize the presence of that cover crop. Yeah, we are generally mowing it, or in some cases, on the lower right picture, we disc it to have a bare soil surface to try to maximize our heat absorbance into the soil and then the re-radiation later at night. A trend that I'm seeing here in California and elsewhere in some systems, especially the wine grape systems, that their growers are wanting to use more and more cover crops and have them present for a longer time in the season, trying to improve their soil health, capture carbon, and all sorts of good things kind of involved as part of the sort of the regenerative farming type practices. And as a consequence, though, they're increasing the frost risk in many areas. So I've talked to a number of growers who've never had a frost occur in their vineyard over the last 25 years, and they're having frosts now once they've changed their cover crop management to have more cover crops. So it is something we do need to be aware of the impacts that they can have. And here's just a graphic that kind of shows the pattern here. So the left scenario, when you have a cover crop, reflects the sunlight, dries the soil, so there's lower conduction of heat into the soil during the day and reduced movement of heat out of the soil at night. And the result is you have lower soil and air temperatures. So that's what this white line is sort of showing us here. This is the this white line that I'm drawing on. This represents the air temperature at night. And then this is the soil temperature. So the idea is that if this is the condition of the without cover crop, when we have a cover crop, we have colder temperatures at this site. Again, without cover crop, less reflection, wetter soil, more conduction of heat, and the result is higher soil and air temperatures. So again, and we have some conflicting needs sometimes in how we manage the ground surface, but if one of our main issues is frost, we definitely need to be careful with that.
This is what.
Okay. So I really like this picture. This is in a vineyard in Argentina that demonstrates really clearly the impact that having water on the soil had on a frost. So what you see, this vineyard, you can see it's sort of divided up into two areas. Foreground suffered bad frost damage, but the background section did not. And why is the difference? Well, they had run surface irrigation in two separate sets. the background had been irrigated prior to the frost, so it had a lot of moisture in the soil. The foreground, they had water scheduled to be put onto this block after the frost. So basically, you're comparing dry ground in the foreground and wet ground in the background. And it really shows very clearly that that small difference in soil moisture really had a very large difference in the resulting air temperatures at the site. So again, a key thing is that if we have very dry soils, that increases the chance of frost damage occurring because it results in cooler temperatures. So then, in summary here, a passive frost protection involves ecological and biological processes, but things that you do prior to the frost event. So this is not something you do in the morning of the frost or the day before. This is all part of the ongoing management to simply create an orchard that is more resilient to having cold damage in the first place, and where you're able to store as much warmth as possible in that system during the frost risk season. So, yeah, this is a little note to people, just how the economic damage of frost can be very substantial. So taking these rather simple steps oftentimes can really prevent a lot of economic headache. Okay. So I'll shift gears now and we'll look at using water for frost protection. So sprinklers here, what are the advantages of these systems? Low energy consumption, low operational costs, and fairly low labor requirement. Disadvantages, high installation cost, and the key one right now, high quantity of water needed. The reality is many parts of California and the rest of the world, it's really hard to justify using these amounts of water, either just due to scarcity or due to the high cost. So this has been a big part of my work, is to help growers understand what alternatives they might have to sprinklers. But in many situations, sprinklers still might be the most viable option, or really the only option. So it's not something that we can just simply discount. There are many locations where it is probably the most appropriate method to protect against frost. But we do have some additional problems. Waterlogging of soils from extensive use. As Ben mentioned, that can definitely be a problem with your avocados. Leaching of nutrients. We have a lot more focus now on things like nitrogen. So if we are applying a lot of sprinkler frost protection, that can create other problems for us. Erosion and hillside situations and other environmental impacts. So they are not systems that are without problems. So that we have to be aware of that too in our design and implementation of them. So some key things to understand, why is it that sprinkling water provides a benefit? Well, as that liquid water turns to ice and freezes, heat is liberated from that process. So that's what we're taking advantage of. But there's sort of an ongoing struggle between two processes. Anytime we put water on, there's going to be evaporation, and that takes away heat from the system. So we get cooling. So we have to make sure that there's more heat being delivered with freezing than is being taken away by evaporation. That's one of the key concepts, and probably one of the main reasons why sprinkler frost protection can fail, because it wasn't managed properly to prevent that evaporative cooling loss. And the key data that we need to know when to start and stop the system is the wet bulb temperature. So if you're not familiar with the wet bulb, when you apply water to the foliage of a crop, for example, there's that initial evaporation occurring. So that temperature that wet tissue can be dropped to with that water is called the wet bulb temperature. So sort of the minimum temperature possible with wet foliage under that condition. So when we first apply water, essentially the foliage will drop to that wet bulb temperature. So we have to make sure that that wet bulb temperature, when we turn this on, is above our critical damage temperature. If we wait too late and turn on the water, the temperature can drop to below our damage temperature, and then we end up causing more damage than we would have if we didn't turn it on. So it's really important to understand that. So this chart just shows you kind of a comparison of the two processes of, well, actually looking at three processes. How much heat is delivered as water in this first part? If we have water of 68 degrees Fahrenheit coming out of our irrigation system, as that drops to 32 degrees Fahrenheit, it delivers 20 calories per gram. So that's how much heat is delivered just from the temperature drop of that water. As that water freezes, then we are liberating an additional 80 calories per gram, but the evaporation per gram of water is about almost 600 calories. So this just points out that we have to have many times more volume of water freezing than we have evaporating. So this is the key thing to keep in mind, is that this whole, we're fighting the evaporation process anytime we put on water. So putting on insufficient volumes of water is only going to create more damage because we don't have enough freezing and compared to the evaporation. So again, how do we know when to start or stop the sprinkler system? Well, the best tool out there to get a local data value to understand that is a handheld unit like this to measure the wet bulb temperature. They're very simple, but the problem is you have to be out there to get this data. They are quite accurate. That is one of the key things to have if our goal is to really have the most precise data possible to know when to turn the systems on and off. The alternative to using something like this would be, let's say, a weather station or other sensor that has a humidity sensor, the air humidity, and from that we can then calculate the wet bulb temperature. The problem with that is that all of those sensors on weather stations, the humidity reading is one of the least accurate ones of all of them. That sensor has a lot of variability. So it's plus or minus, in some cases, 5% or more. So that can really impact the precision of the data we're getting from that reading. So if we're relying upon a value from a weather station that may not even be on our property, we have to keep in mind that that may not tell us really precisely exactly what's happening at our site. So if you really, really are wanting to manage this well, having a wet bulb reading from a simple handheld tool like one of these on your property is probably one of the best investments you can make to really understand the conditions. The other factor which is really important if we're using conventional impact type sprinklers is the frequency of rotation of those sprinkler heads. So there's a lot going on in this chart here, but what it's showing, so the blue line here, this is a sprinkler head that has a rotation frequency of once every 120 seconds, okay? And then the line represents the leaf temperature under that condition. So here, when water is put on, it's warm, but then between the rotations, it gets colder and colder and colder, drops to a minimum temperature here, and then increases when the next pass of that sprinkler happens and more water is applied. The white line represents a sprinkler head that rotates once every 60 seconds, and you can see it also drops down. In this case, both reach this wet bulb temperature, and then increases here and drops again. And then if there was another pass, it would come up here again. So the key one here, though, is this yellow one. So where we have a more frequent rotation, 30 seconds. What you'll notice here is that because the passes are so frequent, there's a more constant wetting of that surface that the leaf temperature never drops down to the wet bulb temperature. That's the key take-home message here. So higher frequency of application, the minimum temperature never drops so much because there's not as much of a gap in time allowing that evaporation to occur on that surface. So if you're having to choose between types of systems to use for, let's say you're using combination for irrigation and frost protection, you want to make sure that you have a system that has a higher frequency of rotation if your goal is to provide good frost protection. So that's just a key concept to keep in mind. Here is a chart that summarizes both that, the rotation effect, duration of rotation, 30 seconds in the first column, 60 seconds in the right column, but now split between two different wind conditions. So this upper part here in the lighter color, this represents conditions of very low wind speed. And so if we have, for example, here, if we're trying to, these are three different temperature ranges where we're trying to protect to. So let's say, for example, we want a system that's going to protect down to 28 degrees under conditions of very low wind. If we have a 30-second rotation, our requirement is 36 gallons per acre. If we have this longer rotation, because that's less efficient, in trying to maintain that foliage temperature, we need to apply more water to make sure that we're not suffering excessive cold. So again, this just shows that with this higher frequency rotation, we can use less water. So it's a great conservation tool. Here, though, look at this lower part here. Now we have a little bit higher wind conditions. What does that higher wind cause? More evaporation. So if we have higher evaporation conditions here, we need to apply more water to achieve the same level of protection as we would under a lower wind condition. So let's compare, again, this condition here, 30-second rotation under very little wind, protecting down to 28 degrees. The same level of protection with the same rotation, but under a higher wind is going to require more water. So that really is the take-home message from this chart, that if we're expecting to be protecting under higher wind conditions, we have to have more water available to do so. And if your goal is to use as little water as possible, make sure you use the quicker rotating sprinkler heads. Now that is largely for applying over the foliage, for many crops. With things like avocados, that may not be practical or useful for you. You may be looking at using an under canopy type sprinklers here. So the goal here is not to have the ice coating over all the foliage, but rather to have it more on the ground. If there's cover crops, whatever might be lower on the surface. So this also is going to be liberating heat in the same way, but it's not going to offer quite the same level of protection as you would if you were able to encase the entire canopy in ice. But for the structures of many of your orchards with large trees, you simply cannot be covering all of those with large amounts of ice. So your best option may be to use this sprinklers or other irrigation under the trees like this. But the same concepts apply, is that you want to make sure that you're putting on far more water to provide heat through the freezing process than you would be losing to the evaporation process. And the whole use of water for frost protection is it's not an area of technology that evolves very quickly, but to me, one of the more interesting recent developments in within the recent decades has been these lower flow type sprinkler systems, which are being used in avocados and other areas. I don't know as much in California, and maybe you can chime in, but they are interesting in that they provide full area coverage at lower application rates than our typical impact type sprinklers. But each individual sprinkler head covers a relatively small area, a diameter of, let's say, about 20 feet approximately. So the advantage that they have for growers is that they use substantially less water than a conventional type sprinkler system. I have questions about how effective they're going to be at very cold conditions. I don't know what work has been done. There may have been tests done already that I'm just not aware of on that, but that's one thing that I would look at. For your situations where these have to be installed or typically are installed above the canopy on large trees, that's really going to be difficult perhaps to make happen. I know I've seen some of these installed in places like Chile, and they typically are installed on some of the smaller structured type trees where they're put over the tops. But I'd be curious to know what the local experience might be in California if something like this would be more applicable. So we can address that more in the discussion later. Okay, so a summary then of sprinkler frost protection here. We're using water, let's say, for frost protection. Primarily we're looking at sprinklers or some type of surface irrigation. But the key concept here is that it's the availability of water is going to be our main driving factor in this decision. And throughout California and elsewhere, that's just becoming more and more challenging. And I don't think that is going to go away. So understand that the protection is from the freezing of water, and that we have to then make sure that we have more freezing happening, more heat delivered by freezing than we have by evaporation. So that's going to be the constant struggle here. So if we want to make sure we have enough to prevent damage, we have to have sufficient volume. One of the other challenges is when we have frosts over multiple days in a row, just having that much water available in the system can be a big challenge to many operations. So there are some limitations here. Okay, I'll change now to just kind of a quick overview of using wind machines for frost protection. Advantage of these systems, relatively low fuel requirements, very low labor requirements. Many of them now are fully automated and low operational costs. The big disadvantages, noise. Noise is becoming a very significant problem. It has been for a long time. And that's something that, in California and many areas, we really haven't addressed sufficiently, but I think that over time we will have to focus on this a bit more. That's something it's really hard to avoid this. Very high initial investment, clearly. Now, these are expensive machines to install, and you really want to understand, are they going to work in your system and provide the protection that you want prior to making this level of investment? The last thing you want to do is buy a bunch of these machines and find out they really are not working well for you. They really only provide a benefit if there's a significant temperature inversion. Because what are they doing? They're mixing the warm air that's up high. In this case, this tower might be about 35 feet high, and mixing it with the colder air that forms on the surface. So this blending of the layers of air is what creates the warming toward inversion, the more warming we're going to get. So here's just a schematic then of how this occurs here. So what we're looking at here, this two lines. So the blue line would be the air temperature profile with height above the ground prior to starting the wind machine. So what this is trying to show you that near the ground surface, what these heights are, near the ground surface is very cold, and yet it gets warmer as we go up above the ground. So that's a common inversion type condition. Then when we turn on the wind machine, that then results in the red line here. So the air temperature near the ground becomes warmer. The air temperature up high actually becomes colder. We don't care about that because our crop is not that high. What we're trying to do is basically take the warm air that's up high and mix it down low to blend the two and end up with the warmer air down near the ground surface, which is what we want. So fairly simple thing. The other key thing to keep in mind is that this effect is really immediate. As soon as you turn on a wind machine, if there is an inversion, you're going to get this benefit. If that wind machine is turned off, it's not going to take very long for the system to revert back to what it was before. So that's the big difference between wind machines and sprinklers is that when, as I mentioned with the sprinklers, you have that whole issue of the cooling effect due to evaporation when the sprinklers are first turned on. There is no similar effect with wind machines. You can wait until you're very close to the damage temperature, your critical temperature, before you turn them on, and you're not going to be penalized in any way by doing so. There's no need to turn them on 10 degrees warmer than your critical temperature because you're creating a level of warming that's probably not necessary and using more fuel and creating more noise for the neighbors. We can combine wind machines with things like water and heaters. So the effects tend to be additive when you use these things together. So under plant sprinklers, what we don't pair is over canopy sprinklers where you're actually spraying onto the foliage with wind machines. And why is that? Well, because now you're evaporating more water by blowing the wind across that condition. So we would only pair wind machines with sprinklers that are applying water or irrigation that's being applied underneath the canopy. Commonly pair wind machines with heaters. That can be a very good combination. If I recall, I have a graphic here that shows this. Okay, now here's talking about wind machines and underplant sprinklers. Well, one of the key concepts is that we start using the water first, okay? And then if the temperatures continue dropping towards our critical levels, then we turn on the wind machines if needed. With heaters, the basic concept is that we place heaters around the outside edge of where that wind machine coverage might be. So let's say a typical wind machine, standard machines, at least in the past would cover about 10 acres or so. So you'd be placing these heaters around the periphery of that wind machine. So this reduces the number of heaters that you would need at the site. And the key point here is to not place heaters near the wind machines, kind of like this picture might show. I don't know if they were actually using the wind machine in this example here, but why would we not want to put the heaters right next to the wind machine? Well, if we're applying heat to the where the propeller is blowing that air, and essentially blowing warm air over the orchard, warm air is more buoyant than cold air. So the effect is that that warm air is going to tend to just float upwards. So having a heat source at the wind machine itself is actually going to reduce the area of coverage from that wind machine. Now, you might increase the level of protection within that small circle that you're covering, but you're going to greatly reduce the area of coverage. So you really want to be careful by heating. Um, Interestingly, several decades ago, there was an effort that a company thought that they could make a wind machine, instead of having an engine turn the machine through a gear system, they had jet engines on the tips of the blades. It's a great idea because now you have these small jet engines like a helicopter uses to spin the blade very quickly, the blades very quickly, and those jet engines provide heat. Well, tests showed that yes, they do work great for a very small circle around the wind machine, but that same effect occurred. That warm air that was being blown down just kind of did a arcing movement upwards. So it reached a very short distance and then just floated away vertically. So again, trying to add heat to the wind source, it's sort of a self-defeating purpose here. But in spite of that, there are parts of the world where they do this. So this is an example of some wind machines I saw in Argentina, and I've seen similar in Chile, where they are putting burners at the base of machines here. I think what they're trying to do, they must have some conditions where the temperature inversions can be very weak in some of these areas on some frost events. So I could understand under that situation where you're basically not going to have much benefit from turning on the wind machine if there is no temperature inversion, that they can at least gain something, some level of protection by adding heat here and getting just a much smaller area of protection. Ben, have you ever seen anything like this here in California? I have not like this yet, but I imagine the fuel consumption costs must be very high. And just mention helicopters, think of them, they're just sort of like a wind machine in the sky, you know, very well positioned, push the warm air downward because they're now above, in some of the warmest air in the system. But just like wind machines, they require an inversion to work. So there's no point in flying a helicopter if you have an advective freeze, and you actually could make things worse by doing that. Uh, for this to work, the passes have to be quite frequent over the field. Talk to the pilot to make sure they know where to fly, and make sure they're focusing on the areas that need it the most. We want to load that machine with water so that it has more weight, because they have to, in order to make the maximum blowing effect downward, it should be heavier to maximize that. And using marker lights in the field to show the pilot where to go to get the maximum benefit from that. You've probably seen some of those sensors that you can buy that have like LED lights that flash in different colors to indicate to somebody who's flying over where the coldest temperatures are. So you would definitely need some tool like that. So summary of wind machines, they are a method of what we call active frost protection, but to work, we really have to have a temperature inversion for them to provide a benefit. They mix the warmer air aloft with the colder air near the ground surface, which is where our crop is. So that's how we get that benefit. But they can be used in conjunction with sprinklers or other irrigation under the plants, and also with different types of heaters. Okay, I'll talk just kind of briefly about ice nucleation and bacteria. This has been an area where I've had a little bit of work with some colleagues on in the past. So the whole concept here of ice formation, it doesn't, when water reaches 32 degrees, that water can freeze, but it doesn't often or necessarily freeze right away. It's when we get water can be super cooled below that freezing point, and it takes something to initiate the formation of those ice crystals. So the two common things would be like a bacteria or bacterial residues. That's actually what initiates those residues in the water itself. And the liquid water is what initiates the formation of ice. The other thing that can initiate the formation of ice is agitation. So this is where we can see some things that we shake. A super cooled leaf tissue that has yet to start freezing, and we shake it vigorously, that can initiate the ice formation process. So we're going to focus primarily, though, here on the role of bacteria. And part of the idea is, well, if it's bacteria on the tissues that are causing this ice nucleation to happen in the first place, leading to the freeze damage, maybe we can do something about this. Maybe we could kill them. Maybe we can introduce something that competes with them, but doesn't itself cause the same problem, or remove some of the sources of these bacteria, which is typically the cover crops, the ground cover. So we'll talk a little bit about these here. So there's a variety of ice nucleating bacteria, just some lists of different types here, but the key thing, these are ubiquitous in our environment, okay? We're not gonna be able to just eliminate these from the world. This is just part of us. And so they exist all around us, and something that we're generally not really paying much attention to, but they are there. How do they affect the formation of ice? Well, a really good example comes from the world of artificial snowmaking. So there actually is a bacteria, dried protein from the Pseudomonas syringae bacteria, which is sold to the snowmaking industry. By injecting this along with the water through these snowmaking machines, they can now produce snow at 27 degrees Fahrenheit rather than 15 degrees Fahrenheit that would be required if they didn't have this ice nucleator within this sprayed water source. So it just really shows, the presence of this ice nucleating bacteria has a huge impact on the temperature at which ice nucleation starts. So it's even in a commercial use like this. So that then raises questions. Well, one possibility could be that we use a competing product, a competing type of bacteria that displaces the bad ice nucleating types. So one product that's sold, and I do not know if this has any use on avocados, but it's used in other tree crops, fruit crops, as a frost mitigation tool to reduce frost damage. So it's another type of bacteria that colonizes and displaces the ice nucleating type bacteria, and can be, one approach. We'll call this sort of a semi-passive approach, because clearly you're not going to put this on the night before a frost. Something you have to put on well prior to frost to kind of create a condition where you don't have large amounts of ice nucleating bacteria on the crop itself. But we're finding in vineyards and other crops, the biggest source of these ice nucleating bacteria is not the crop tissues themselves, it's the cover crop, primarily the grasses, hold and host a large amount of these bacteria. Whenever we go in and mow or do other disturbance to that system, we are releasing large amounts of these bacteria into the air, which then get onto our crop tissues. So we have to be cognizant of that. If we're trying to manage cover crop residues or weed residues, other vegetation at times of high frost risk, we may inadvertently be creating a condition of coating our vine or orchard tissues with these bacteria, leading to higher frost risk. So that's something that it's an ongoing area of study to understand how can we better manage these systems to just try to avoid this type of interaction. Okay. Well, now I'll kind of go into my kind of final topic here, an area which I've been working on quite a bit, measurements of inversion conditions to help us understand how to better use wind machines. So this is kind of repeating a little bit some prior information, but again, I want to point out the importance of understanding the type of frost event that we have, this radiation frost versus advective type frost. So on the left, this is an air temperature profile representing a radiation freeze, where cold air near the ground surface and the air temperature increases with height above the ground. And if our crop tissue is about this height, then we clearly have some warmer air above the ground that we can take advantage of to try to warm our crop. Under an advective freeze, this might be the pattern that we see. In this case, it's sort of a worst case scenario where it just gets colder and colder with additional height above the ground. So these are sort of the two extremes, but of course we can have any number of conditions in between these two. So how do we know what we've got? Well, we can measure them. Now, we don't have to measure the entire height of this profile, at every 6 inches. We can just put a sensor down near the crop level and then a sensor up at some higher level. And then comparing the data from those two. And that'll give us a pretty good picture then of what type of condition we have. And then how do we use this information? Well, this is the basic relationship between what we call the inversion strength. So inversion strength is just the difference in temperature between the two heights that we're measuring. For example, 35 feet and 5 feet. Whatever that difference in temperature is, that's the inversion strength. So typically it's going to be warmer up high. Let's say if it's 4 degrees warmer up high and down below, then we have our inversion strength is 4 degrees. And there's a linear relationship between the increasing value of that inversion strength and the warming effect from a wind machine. So if we have conditions of very weak inversions, like down here, the wind machine just does not provide very much warming. The stronger the inversion, the greater the warming effect. So there are different types of wind machines. You're all familiar with these permanently installed tower types. In a lot of our shorter crops, we make use of these portable machines. And there's even some much lower powered portable machines that we're using in some areas as well, which may have a fit for areas where you just don't need the coverage of a much larger machine. And what's interesting, this lower machine here, it can also be set to oscillate. So instead of turning a full 360 degrees, it can just be oscillate over a narrower range, which in some cases could be a nice tool to have in some situations. Price-wise, they're actually fairly similar, so you have to make sure that you're getting the right tool for your location here. But the technology of wind machines has not changed a lot in the past decades. It's a fairly mature technology. So if I'm going to measure the temperature inversion conditions to help characterize frosts and frost risk at sites, there's probably two very different approaches that we can make. The first approach is a fairly short-term, very site-specific, dense measurements at a specific location to understand the conditions at that site. This is very cheap and easy to do. I'll show you an example of how we do that. The disadvantage is that the data is not available in the moment. We don't know what the data is until we dismantle all of the towers that we use and we can look at the numbers. So that's a common complaint I get from my farmer cooperators. Say, well, Mark, I'm glad you're doing this, but boy, I'd really like to see in the moment what is happening here. This type of inexpensive measurement does not allow that. The other issue is, when we do this, it's usually just for a short time, 1 or 2 years typically. And then the question is, well, is that representative of what the frost conditions or the inversion conditions are going to be like in the longer term? The only way we know that is to take measurements for a longer time. So the other option, more of a permanent type measurement with a tower over a broader region with real-time data. Everybody likes to have this real-time data. The problem is it's much more expensive to install this equipment, much more expensive to operate. But the other advantage is we can use the data for other things. Basically, we're talking about a weather station with a tower attached to it. So there's other benefits from having that system in place. So here's an example of the less expensive short-term assessment here. So that's a picture of me on the right here, just for scale. You can see this is setting up a 35-foot tall tower. This is just a very inexpensive, flexible pole cobbled together from parts from Home Depot with 2 inexpensive data loggers that measure the air temperature, one at 5 feet height, the other one up the top at 35 feet tall. The tower itself costs a little less than $100 to put together, and then the 2 data loggers add another close to $200 to that. So it's a very inexpensive tool that can be used repeatedly at many different sites to collect this type of inversion data. So the diagram on the left just shows you an example of how at a certain location in Santa Barbara County, where we did a simple study with a grower, that area in blue is the area where they were typically using frost sprinklers in the past, and they wanted to know, could they replace those with wind machines? So I put out towers. That's what those 8 stars indicate, where I took the measurements with these towers. And then from that data, was able to show them some results. This is what we got from that site here. So what you see on the left, that chart, this is a track of the air temperature over about 5 days from one of those towers. So what you can see pretty clearly, I hope, is that when the values are high here, that's the daytime condition. So it's warmer near the ground, colder up high. And then at the nighttime here, that black line, that's the air temperature near the ground. And you can see it's substantially colder near the ground than it is up at 35 feet. So over a number of nights here in a row, you can see there's a very substantial difference in temperature of about, let's say 6 or 7 degrees oftentimes. That's a pretty strong inversion to have. So based on this data that we saw consistently at this site, that landowner then went ahead and purchased a number of these wind machines to install in that area. So does this guarantee that it's going to be effective in all events? Of course not. But at least it gave us pretty good idea that when we have cold temperature events, that the inversions can form at this site. And that gives us some pretty good confidence that the wind machine can provide a pretty solid benefit. This is an area where there's not a whole lot of wind machines being used. So once we kind of get a feel for this, once other growers see this in place, that might then give them the idea that, hey, this could be an option for them too. And maybe they can free up some of their water for other purposes. So that's really the incentive to look into this. So how I work with growers, I can provide them instructions on how to do this themselves. In some cases, I can provide the towers to them as well. And what I really can help them out with, though, I can loan them the data loggers and do the data processing for them. So if they spend the $100 to put up their own tower, like you see on the right, then I can just simply send them the data loggers and that little white housing that you see that shields the data logger. They simply attach that to the tower and then erect the tower, run it for whatever 3 months during the frost period, take the tower down, send me the data loggers back, and I give them the data. So it's been a real easy way to work with people, and I've done this with people in other states. And really, it has been a great tool to really get some ideas on what these inversion conditions are like. And like the previous slide showed, to really give people some level of confidence that that the data supports the idea of investing in a wind machine at that site. Because if we don't have this data and we're in an area where there's really no industry knowledge of the use of wind machines, we're having to guess a lot. That's what I'm trying to avoid. But then here's the other option, again, kind of responding to industry requests to have data like this live in real time so that everybody can use in the region. So I've over a number of years in different areas, I've been installing weather stations like this that have one of these flexible poles attached to them. So really, it's just a conventional weather station that measures, the rainfall, air temperature, humidity, wind speed, solar radiation. And then the difference is, though, we add a tower. So those portable towers that I was using in the previous example, those tend to be 35 feet high. I use the same thing, but I shorten them down to 30 feet just because, again, I'm using materials from Home Depot that were never intended for this use, and they can suffer damage from wind if we have strong wind. So I shorten them down a little bit to be a little bit more resistant to the wind. And that has worked actually very, very well. And a 30-foot height is very sufficient to get good information on these inversions. I currently, in San Luis Obispo County, have 20 of these stations installed. I'm using a company called the Western Weather Group to manage the data. They've been great to work with. They present the information in a very accessible way to growers. I'll show you the website link at one of my last slides here so you can see where it's at. But here's just a snapshot of one moment in time. And so what this reports is the inversion value is the difference in temperature between 30 feet and 5 feet. So for example, if we have like here in the station here 5.7, that means the 30-foot sensor was 5.7 degrees warmer than the 5-foot sensor. Okay. So one key thing you can see here, well, there's a lot of variability in this condition amongst these sites. So it's not a situation where everything is going to read uniformly. And why is that? Well, you could have differences in wind occurring in different areas. For example, this may have been stronger winds through this area here. These four stations are in more of a coastal area here. This one here in Morro Bay, near the avocado production area. So it's really a reflection of the local conditions. Now, in all cases, I've tried to put these weather stations in the types of areas where we would expect frost to occur. So some of the lower parts of the fields, flatter areas, trying to capture that frost condition. So but again, I'm kind of dependent. All of these are installed on private property with landowners' permission and consent, but I often don't have the ability to choose exactly where I'd like to put them because I have to work around their farming operations. But I think so far it's given us some really interesting coverage of what is going on with the inversions in the area.
Say, Mark, a question
Yes.
just came up. Would it be worthwhile to place these sensors on the wind machines themselves and use that temperature difference to indicate when to turn it on?
Yeah, no, that's an interesting idea. The nice thing about doing that is that with the wind machine, especially a towered machine, you already have a tower in place that's always going to be there. I could see that as being a good approach. It would give you data that's of use probably maybe up until the point when the wind machine is turned on. Once it's on, now you can be mixing things. So then what you're measuring is, well, the conditions of the mixed product. Okay. So what I'm doing, all of my stations, they're installed far away from any wind machines because I want to see what the natural conditions are like that are not being affected by a wind machine. So again, I think that having that additional sensor, a lot of these wind machines now include a temperature sensor on the device itself to tell it when to start, when to turn on. So you could easily put a second sensor up high on the tower to give you that additional information. And let's say, for example, that additional sensor showed that there was no inversion, or you had an advective freeze where it was actually colder up high, that could then be used to tell you, do not turn this on. So that certainly could be a useful thing. And so I'm certainly happy that if anybody would like to work to do that, we could do a little concept trial where I can loan you some small data loggers and you can climb up that tower and add them to your machine, and we can then see what does the data look like. Now, I don't talk on one topic here. I should address it now. So there's the whole when we measure air temperature on a weather station, we have that temperature sensor shielded inside this ventilated white thing called a radiation shield. So that's an important thing to keep in mind. Why do we do that? Well, during the daytime, we want to keep sunlight off of that temperature sensor. If we didn't have that shield, that sensor might heat up to 150 degrees and we get nonsense data. At nighttime, that shield still has a role. It protects that sensor from being exposed to the sky at night. So an object which is not shielded, which is exposed to the sky, will actually get colder than the air if the sky is clear and there's little wind, like a radiation type frost condition. Well, one of those objects that gets colder than the air is our plant tissues. So in grapevines, for example, the leaves of a plant which is exposed to the sky at night might be 2 to 4 degrees colder than the air. So why this concept that it has been known for a long time. Typically on the wind machines, if they're using a sensor to tell that machine when to turn on, that sensor is not put inside one of those white shields. Often it's just exposed to the sky the same way as, let's say, a grapevine shoot or another crop shoot would be. So we want to make sure we're comparing similar types of sensors. So that's what I want to drive home here. So if you're comparing a sensor on your wind machine that is already included. It's a bare sensor. You need to put a similar bare sensor up high as well. Or we add two additional sensors, both with shields, one at the crop level and one up on the tower. So just want to make sure we have to compare apples to apples here. Okay, so this chart now shows you some of the nice thing about this weather station network is that all the data for the last several years that I've been running it, it's all available. You can look at live data, you can produce charts like this from historic data. Part of the goal of doing this is that I'm creating for the industry sort of a database of these inversion conditions so that even if we may not have the need today to know whether or not we have the right conditions to invest in a wind machine, but maybe the next guy in 5 or 10 years might have that need. So building up this data set, this could be very valuable. And this just shows you then that some of the data for a year and a half ago, we had some very cold temperatures in the spring of 2022, just to kind of show you some of the patterns. So here, the blue line, what we're looking at is from air temperatures on one night from midnight up until 8 a.m. And that blue line, that's the air temperature at 5 feet. The red line, the air temperature up at 30 feet. You can see very clearly there's an inversion because it's warmer up high. This is the coldest, one of the coldest locations in the county. Okay, so you can see it got down here at about 22, 23 degrees on that night. So it just gives you an idea of, some of the challenges that we deal with in some areas here. The positive thing that, yes, we had a good temperature inversion through that time, but if our goal was to grow a frost-sensitive crop at a site like this, even with the warming benefit from the wind machine, we're still going to be below the critical temperature of something like grapes or other frost-sensitive crops. So this is part of the reality, what we want to measure here. And not only do we want to know, what the inversion condition is, but we want to know if a wind machine is operating under that condition, can it provide enough benefit to protect a crop? And so a site like this presents some serious challenges for that. The other nice thing about having the inversion data on a weather station is now we can look at other factors that relate to inversion, like the wind speed. So here's another site, looking again on a morning of April. Temperatures are getting fairly cold, not quite down to freezing, but still pretty cold. You can see in that upper chart, that's showing you the inversion, that the air temperature at 30 feet is consistently warmer than the air temperature down at 5 feet. So it tells us we had an inversion, even though it's maybe not super strong, it's a little bit inconsistent. And I've been trying to look for reasons to explain why at some periods it gets a little weaker, like right in here, what is going on. Oftentimes that can be caused by the wind picking up during the night. And here's some of the wind data. Now, that doesn't really seem to correlate super well here, but again, it just gives us an idea. If we saw a condition where the wind was picking up a lot during the night, then the inversion probably would get smaller and smaller. Or if the wind completely stopped, then the inversion gets stronger. So one of the reasons why just the inversion is sort of a moderate inversion through the night here is that we had appreciable wind through the night, just this soft breeze blowing, which is probably enough to mix the air to prevent the really strong inversion from forming. And then just another example from another site, different morning, again here in May last year, showing the types of inversions that can form. This is a pretty substantial inversion at this site. So again, this is the kind of information that if a grower in this area is looking to invest in wind machines, that having some confidence that this type of condition tends to occur during these frost events or near frost events would be a really important thing to have as part of that process. Okay, so here's the website for that. And if you would ever like to see any more examples of how it can be used, feel free to contact me. I've got other information on this on our website that can show you some other uses of this data. But I really think it's really been kind of a game changer for us to really have some solid data to understand in far more detail what our frost conditions are and how we can respond to them most effectively. Because it's, again, the whole idea is that we want growers to have the best data possible to make informed decisions on what types of tools that they use, what types of strategies that they use. Okay, well, that's all I've got for you. I'll go back to swim. So thank you very much. Ben, I'm happy to
Wow, wow, wow.
start chatting.
I've got a lot of questions.